This is a video from section 8.3 in linear algebra, and it's based off the lecture notes. A linear transformation T that maps U to V that is both one-to-one and onto is called an isomorphism. U and V are said to be isomorphic. Isomorphic vector spaces have the same, quote, algebraic form, even though they may consist of different kinds of objects. Okay, let's take a look at an example. The following diagram illustrates an isomorphism between P2 and R3. And remember, P2 is the set of all polynomials of degree less than or equal to 2. So I'm going to take C0 plus C1x plus C2x squared, and I'm going to map it to C0, C1, C2. And I claim this will be an isomorphism between P2 and R3. And this would be good to check. Now, theorem. Every n-dimensional vector space is isomorphic to Rn. This is a very interesting result, okay? Now, proof. What we're going to do is let V be an n-dimensional vector space. To show V is isomorphic to Rn, we must find a linear transformation T that maps V to Rn that is both one-to-one and onto. So here's how this works. Let S, which is the set containing the vectors v1, v2 through vn, be any basis for V. And what we're going to do is let T map V to Rn, where T of U is equal to the coordinate vector of U relative to S. And what we want to show is that T is one-to-one, T is onto, and T is a linear transformation. We're going to show all of those things. And if we could do that, then we can say that V is isomorphic to Rn. So in the first step, we want to show T is one-to-one. And so this is what I'm going to do. Let U and V belong to V, where T of U equals T of V. To show T is one-to-one, we need to show that U equals V. Since U and V belong to V, there are scalars C1 through Cn and K1 through Kn such that U equals C1V1 plus C2V2 plus all the way through until CNVN. Also, V is equal to K1V1 plus K2V2 plus all the way through until KNVN. Okay, and so in other words, U can be written as a linear combination of the vectors in S, and V can be written as a linear combination of the vectors in S. And moreover, it can only be done in a unique way. Okay, only one way. Now, remember, T of U is the same as T of V, which says the coordinate vector of U relative to S is the same as the coordinate vector of V relative to S. So what that says is the C1, C2 through Cn, that vector, is the same as the vector K1, K2 through Kn. Okay? And the only way that can happen is if their corresponding components match. Remember, two vectors are equal if the components match. So what that says is C1 equals K1, C2 equals K2, ... Cn equals Kn. And that says C1V1 plus C2V2 plus ... plus CNVN equals K1V1 plus K2V2 plus ... plus KNVN. but that just tells me U equals V. And therefore T is 1 to 1. Now, we want to show T is onto. Let A1, A2, A3 through AN belong to Rn. Choose W, which is a linear combination of the vectors in S, where the coefficients of V1, V2 through Vn come from this vector in Rn. So, in other words, I'm going to choose W equal to A1V1 plus A2V2 plus ... plus ANVN. And that belongs to V, right? Now, T of W is the coordinate vector of W relative to S. And that is the vector A1, A2 through AN, right? And that's because of the way I structured W. And so notice how we got the vector back. And that shows T is onto. So let me say that again. We pick something in Rn, and I'm going to call it the vector A1, A2, A3 through AN. That belongs to Rn. I'm going to choose W equal to A1V1 plus A2V2 plus ... plus ANVN. That belongs to V, for sure. T of W is the coordinate vector of W relative to S. To get the first component, I look at A1. To get the second component, I look at A2. To get the last component, I look at AN. Right? And that's exactly what I'm supposed to get. And that shows T is onto. All right, now, let U and V belong to V and let K be a scalar. Since U belongs to V, there exists C1, C2 through Cn such that U equals C1V1 plus C2V2 plus ... plus CNVN. And since V belongs to V, there exists scalars D1, D2 through Dn such that V equals D1V1 plus D2V2 plus ... plus DNVN. So I can write U as a linear combination of the vectors in S, and I could write V as a linear combination of the vectors in S. Now, let's take a look at U plus V. Now, I claim that that's going to be C1 plus D1 times V1 plus C2 plus D2 times V2 plus ... plus Cn plus Dn times Vn. Now, what I want to do is I want to look at T of U plus V. But that's the coordinate vector of U plus V relative to S. And that is the vector whose first component is C1 plus D1. The second component is C2 plus D2. And then I keep going. The nth component is Cn plus Dn, right? And that comes from up here. So notice how the first component is C1 plus D1. The second component is C2 plus D2. And then I follow that pattern. And then the nth component is Cn plus Dn. But can I write this as the vector C1, C2 through Cn plus the vector D1, D2 through Dn? But that's the coordinate vector of U relative to S plus the coordinate vector of V relative to S. And that's T of U plus V, T of V. Let me say that again. We get the coordinate vector of U relative to S plus the coordinate vector of V relative to S. And that's T of U plus T of V. And so T of U plus V is T of U plus T of V. Now, take a look at T of KU. But that's T of K times C1V1 plus C2V2 plus ... plus CNVN, right? but that's T of K times C1 V1, so I'm distributing, right? So I get T of K times C1 V1 plus K times C2 V2 plus dot 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 plus K times Cn Vn. But that's T of KC1 V1 plus KC2 V2 plus dot 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 plus KCN Vn. So I just shifted the parentheses. But that's the coordinate vector of Ku relative to S, which is just going to be the vector Kc1, Kc2 through Kcn. So notice I'm just looking at the first component, right, is Kc1. The second component is Kc2. The nth component is Kcn. But I could pull the K out and multiply by the vector C1, C2 through Cn. But that's K times the coordinate vector of U relative to S. But that's K times T of U. And so after all that work, T is a linear transformation, and we have thus shown that V is isomorphic to Rn. So what did we do? We constructed a mapping from V to Rn and showed that that mapping was one-to-one onto in a linear transformation. And if you could do that, then those two vector spaces structurally preserve the same properties, essentially. So, okay, this will do it for this video for section 8.3. This was based off the lecture notes, so this will be part 1. All right, thank you.